Hello students. In a series of kinematics of circular motion, this is our fourth video. In this video, we are going to discuss radial acceleration in case of uniform circular motion. For that, let's take an example of a satellite revolving around the Earth. These are the different positions of the satellite during its motion. Let V1, V2, V3, V4, V5 and V6 are the instantaneous velocity at different positions. At the given instant, the instantaneous velocity has tangential direction. This tangential direction of the object or the satellite is due to its inertia. Therefore, the object or satellite would move along the tangent. But we observe student satellite is not moved tangentially. Therefore, there must be presence of some force which act on the object or satellite which changes the direction of the velocity at that point. This force is known as the centripetal force and the acceleration is the radial acceleration or centripetal acceleration. Let's discuss more about this acceleration. Note down student, the centripetal acceleration is necessary for circular motion. The centripetal force is responsible for the change in the direction of motion. That is, the change in the direction of velocity. So for the circular motion, we know student, direction of motion changes at every position. So that it is necessary for for any circular motion, centripetal acceleration is necessary. Without this acceleration, circular motion cannot possible. So I again repeat student, for any type of circular motion, whether it is uniform or non-uniform circular motion, the centripetal acceleration is necessary. Now let's find its formula. For finding the formula of a change in velocity, let's consider the satellite moves from position A to position B in time delta t. Delta theta is the angular displacement of the satellite. Delta r is a change in the direction of a radius vector. V1 is the velocity at position A. V2 is the velocity at position B. Now student, what I'm going to do is, without changing magnitude and direction of velocity V2, I draw it at position A. So according to triangle law of vector addition, we have delta V, that is change in the velocity. In the geometry of a circle, the angle between radii is equal to angle between its tangent. Therefore, the angle between velocity vector V1 and V2 is delta theta. Here we can see student, the change in velocity vector delta V is perpendicular to the delta r and directed almost towards the center. Now student, let's find the magnitude of change in velocity. For that, redraw the triangle of velocity vectors. From this triangle we can write vector delta V is equal to vector V2 minus V1. Delta V, which represents the magnitude of a change in velocity, is equal to modulus of a vector V2 minus vector V1. As the given motion is a uniform circular motion, therefore the magnitude of velocity is constant. Therefore, magnitude of a V1 is equal to magnitude of a V2 is equal to V. Let's use formula to find the magnitude of a vector, which is delta V is equal to under root of V square plus V square minus 2V square cos theta, where theta is the angle between two velocity vectors y's V1 and V2. Therefore, delta V is equal to 2V square minus 2V square into cos theta. Take 2V square common. In a bracket, we have 1 minus cos theta. 1 minus cos theta is equal to 2 into sine square theta by 2. Let's substitute the value. Delta V is equal to under root of 2V square into 2 sine square theta by 2. After complete multiplication, we have a delta v is equal to under root of 4v square sine square theta by 2. Finally, we have a delta v is equal to 2v sine theta by 2. This is a magnitude form of a change in velocity. This form is not useful to represent the change in velocity in a vector form. It is because, student, even delta v is a vector quantity, but for the finite time, theta, that is angular displacement, is not a vector quantity. Now let's represent this change in velocity in vector form. For that, we have to consider the motion of the object for a very small interval of time, dt. Let's suppose that the satellite moves from position A to B. d theta is its angular displacement in time dt. dr is the change in the direction of a radius vector. Let v1 is the instantaneous velocity at position A. v2 is the instantaneous velocity at position B. Using this velocity vector v1 and v2, I complete the triangle, whose angular displacement is d theta. Reconsider the equation delta v is equal to 2 into v into sine theta by 2. For delta t tends to 0, sine d theta by 2 is approximately d theta by 2. Now let's take limit of above equation. Limit of average velocity as a delta t tends to 0 is equal to 2 into v divided by 2 into limit of average angular velocity as a delta t tends to 0. From this, we have a dv by dt is equal to 2 into v divided by 2 into d theta by dt. 2 gets cancelled. We know, student, the rate of change of velocity is acceleration, and that of rate of change of displacement is velocity. So here dv by dt gives us acceleration a, which is equal to v into angular velocity omega. This acceleration is known as radial acceleration or centripetal acceleration. Let's discuss the direction of this centripetal acceleration or radial acceleration. For that, let's observe this diagram. Here you observe, student, vector v2 and that of a vector dr are in the same direction. Vector dv is a perpendicular to the vector v1 and a vector v2. Remember, student, this possible only when we consider the motion for a very small interval of time. Similarly, vector dr is a perpendicular to the vector r1 and vector r2. Again, the same thing. This condition is true only when we consider the motion for a very small interval of time. From this 2, we can write, student, vector dv is a perpendicular to the vector dr and directed towards the center. So, student, the vector dv is exactly directed towards the center only when we consider the motion for a very small interval of time. Therefore, the rate of change of direction of velocity is called radial acceleration, as it is directed along the radius towards the center. Vector ar is equal to vector dv by dt. Now you may understand, student, why the name of this acceleration is radial acceleration. It is because, student, the given acceleration is directed towards the center along the radius. Hence, it is known as a radial acceleration. One more name is for this acceleration is a centripetal acceleration, as this acceleration is directed towards the center. But one more thing that you have to remember, student, the acceleration vector, even though it is along the radius, it is direct towards the center, and that of a radius vector is always direct away from the center. So the acceleration vector and that of a radius vector both always are in opposite direction. Now, in a uniform circular motion, the rate of change of direction of velocity is constant. That is, radial acceleration is constant. Now, let's represent this acceleration in the vector form. As you can see in the diagram, student, instantaneous acceleration is directed towards the center of the circle, and that of a velocity is a perpendicular to the acceleration, and that of angular velocity is perpendicular to the plane containing velocity vector and that of the centripetal acceleration vector. From this, we can write vector AR is equal to vector omega cross vector V bar. Now, curl your right hand finger from the vector omega to velocity vector. The outstretched thumb gives you the direction of a acceleration, that is centripetal acceleration. According to Newton's second law, force is equal to mass into acceleration. This acceleration is a centripetal acceleration or radial acceleration. So let's substitute the value of a radial acceleration. Therefore, vector F is equal to m into omega bar into V bar. As you can see from this vector relation, student, F bar is also having the same direction as that of a centripetal acceleration. Hence, the given force is known as a centripetal force. As the centripetal acceleration is a constant in a case of a uniform circular motion, the centripetal force is also constant in a uniform circular motion, and both having the same direction, that is along radius towards center. Hope you understand the concept, student. In our next video, I'm going to give you the important characteristic of the uniform circular motion. And next to that, we are going to consider the application of the centripetal forces. Till then, student, goodbye, take care, and do like, share, and watch my videos. Thank you.